So I want you to imagine something for a second. If you take a completely empty box,
Right.
you pump out every single molecule of air.
Every last atom.
Yeah, every single one. And you block every photon of light. You shield it from all the background radiation out there, and you just, seal it shut tight.
Classical physics would say you have absolutely nothing in there.
Right. Just everyday common sense tells you that you are holding a true empty void. Nothingness.
A completely dead space.
Exactly. But according to the really groundbreaking 2026 physics papers we are diving into today, well, that supposedly empty box actually contains enough bubbling, chaotic energy to theoretically collapse the universe.
It really is the ultimate paradox in modern theoretical physics. I mean, we've spent a century mapping out the universe, right?
Oh yeah, from the microscopic dance of quarks all the way to the massive slow-motion collisions of galaxy clusters.
Right, but the most confusing, mathematically hostile environment we have ever encountered isn't inside a black hole. It's not inside a dying star.
It's inside absolutely nothing, empty space itself.
Exactly.
So today, we are unpacking two highly anticipated foundational documents. They were both authored in 2026 by Riccardo C. Storti, and they're titled Integrating General Relativity with the Quantum Vacuum, Methods 1 and 2, along with their accompanying derivation charts.
And the mission of this deep dive is incredibly ambitious.
It really is. We are looking at a potential solution to a century-old physics problem. Basically, the unification of Albert Einstein's general relativity with quantum mechanics.
Which, for anyone who has casually followed physics over the last few decades, this is essentially the holy grail.
The ultimate prize. Because general relativity, it perfectly describes the heavy stuff. Gravity, planets, the curvature of space.
Right. And quantum mechanics perfectly describes the microscopic stuff, like atoms, subatomic forces, all that.
But when you try to smash their math together, it just shatters. It completely falls apart.
It literally breaks down into infinities. Physicists actually call them ultraviolet divergences.
Ultraviolet divergences, that sounds like a sci-fi movie title. It does, yeah. But basically, if you try to calculate the gravitational field of an electron using quantum rules, the equations suggest that in incredibly small spaces, the energy levels just shoot up to infinity.
And infinite energy in a localized space that means physics simply stops working, right?
It does. To get around this, the mainstream physics community has spent decades relying on some incredibly dense, highly complex mathematical workarounds.
Yeah, the primary method is a process called renormalization, which, to put it somewhat bluntly, is a way to mathematically sweep those infinities under the rug.
That's a good way to put it. They sweep them under the rug so the equations can just limp forward and give us usable answers.
It's like balancing a checkbook by just, erasing the debts you don't want to pay.
Exactly. But the goal of Storti's framework, which is called electrogravimagnetics, or EGM, is to eliminate those mathematical infinities completely.
Completely. No sweeping things under the rug. No arbitrary mathematical band-aids.
Right. EGM uses a process called harmonic quantization to build a bridge from the subatomic scale all the way up to the cosmic scale.
And sticking with us on this journey means that by the time we wrap up, you will understand how measuring the exact physical dimensions of a tiny invisible proton can successfully predict the expansion rate of the entire observable universe.
The sheer audacity of that claim is really what makes these papers so compelling.
It's huge.
It is. The author isn't just offering a new philosophy of space. The math and the empirical evidence provided in the sources actually back the theory up, using data from real-world laboratory experiments and satellite measurements.
Okay, let's unpack this from the ground up, starting with that empty box we were talking about.
The void.
Yeah, the void. If I empty the box completely, and I'm left with what physicists call the quantum vacuum, what is actually inside it? Because the source material redefines empty space entirely.
It does. It's not a void. It is described as a dynamic, effervescent sea of continuous activity.
Effervescent, like a freshly poured soda.
Effervescent is the exact word they use, actually. At every single coordinate of space-time, down to scales so small they defy human imagination, there is a continuous, violent churning of energy.
A churning soup.
Right. And the framework relies heavily on something called the creation-annihilation process, or CAP.
CAP. Okay, how does that work?
In this process, virtual particle pairs are ceaselessly popping into existence. They borrow a microscopic fraction of energy from the vacuum to briefly exist.
Just for a fraction of a millisecond.
Even less. And then, almost in the exact same instant, they collide, annihilate each other, and return that energy back to the vacuum.
Wow, so it's literally a boiling soup of virtual particles appearing and vanishing in a fraction of a second.
Ceaselessly.
But, I mean, this isn't just some abstract chalkboard math, right? The sources lean on real, physical proof that this boiling soup exists in reality. They bring up things like the Casimir force and the Lamb shift.
Yeah, the Casimir effect is probably the most tangible way to visualize this. Imagine placing two incredibly thin, uncharged metal plates inside a perfect vacuum.
Okay, uncharged, so no static electricity or anything pulling them together.
Exactly. And you bring them so close together that the gap between them is barely the width of a few atoms.
Oh.
In a classical universe, nothing should happen. They are uncharged and sitting in a void, but in reality, they are actually pushed together.
Pushed together by what?
By the vacuum itself, because the space outside the plates is boiling with these virtual particles, but the gap between the plates is too small for the larger waves of these particles to pop into existence.
Oh, I see. So there's physically less room for the big particles to form between the plates.
Exactly. So there are simply more particles bumping against the outside of the plates than the inside, creating physical pressure.
That is wild. It's actual physical pressure from empty space.
It is. And that background, that baseline boiling state where these particles are just churning away undisturbed, is called the zero-point field, or ZPF.
The zero-point field. So this is like the floor of reality.
It is the ultimate ground state of reality, yeah. It is the minimum possible energy level required to sustain this continuous creation and annihilation. It cannot be cooled down, and it cannot be emptied any further.
This actually brings me back to the paradox of the empty box we started with.
Right.
If I have this infinite ocean of particles popping in and out of existence with all this incredible energy, why doesn't space just rip itself apart?
That's the million-dollar question.
Because, like traditional quantum electrodynamics, or QED, says that because you could theoretically have virtual particles of incredibly high frequencies, meaning insanely high, near-infinite energies emerging from the vacuum, every single point in space should contain infinite energy.
It should.
The vacuum should just collapse into a universe-swallowing black hole instantly, shouldn't it?
Yes. Physicists call that the infinite energy in a vanishing volume problem.
Catchy.
Yeah. QED allows the math to run away to infinity because there is no built-in limit to how energetic a virtual particle can be. But Storti's framework actually halts this runaway train.
How does it do that?
In equation 18 of the source material, the math proves that in a state of flat space-time, meaning deep space, far away from any stars, planets, or matter, the probability of creating these arbitrarily high-frequency, super-energetic particles drops off to absolutely zero.
Oh, wow. So the vacuum basically has a built-in mathematical speed limit.
Exactly.
As long as it is left completely alone, the bubbling activity stays capped at a manageable baseline energy.
It remains perfectly stable in its lowest possible energy configuration, the ZPF. The math limits the frequency spectrum based on the actual energy density present.
So the vacuum isn't an infinite well of doom.
No, it is a physically grounded, finite energy substrate. But that baseline stability only lasts until we introduce something into the environment.
Right, until we drop a planet into the boiling soup.
The moment you place a massive object into the quantum vacuum, the rules of the environment change. The mass of the object forces the surrounding vacuum into a new, elevated energy state.
It has to work harder.
Exactly. And this interaction, the mass of an object forcing the quantum vacuum uphill, is the mechanical root of what we actually experience as gravity.
Okay, let's talk about that transition. Because if you ask anyone with a passing interest in physics to explain gravity, they will immediately bring up Einstein.
Of course.
We all know the classic visual. Space-time is a stretched trampoline. You drop a bowling ball on it, the fabric of the trampoline sags into a curve, and if you roll a marble, it spirals down the curve toward the bowling ball.
Right, the bowling ball on the trampoline.
Gravity is just the invisible geometric curvature of space-time. But the source material contrasts Einstein's classical gravity with the quantum vacuum theory, which was pioneered by Heisch, Rueda, and Puthoff.
Einstein's geometric model is brilliant, obviously, and it has passed every macroscopic test we've ever thrown at it.
Sure.
But treating space as a smooth, curving fabric is exactly what makes it incompatible with the chunky, discrete world of quantum mechanics.
Because quantum mechanics is all about tiny, individual packets of energy.
Exactly. So the alternative offered in the sources is the polarizable vacuum, or PV model. It replaces the geometric interpretation of gravity with an optical one.
An optical one.
Yeah. Instead of matter curving a fabric, matter polarizes the quantum vacuum.
Okay, polarizing the vacuum. I really need to visualize this. A star sits in empty space. The space is filled with these virtual particles constantly appearing and disappearing. How does a star actually polarize them?
Well, according to quantum electrodynamics, any mass with an electromagnetic profile, even down to a single tiny electron, interacts with the virtual particles around it.
Okay.
An electron has a negative charge, right? So it attracts the fleeting virtual positive charges from the vacuum and repels the virtual negative charges.
Because opposites attract.
Right. And this segregation biases the vacuum. It elevates the zero-point field from its resting state and creates a gradient. The energy density of the vacuum actually changes.
Oh, I see. A density gradient. So the vacuum basically gets thicker or more energetically dense the closer you get to the star. And it thins out, returning to its baseline resting state. The further out into deep space you travel away from the star.
Thicker and thinner is the perfect way to think about it. And this density gradient alters what physicists call the refractive index of spacetime.
Which is denoted mathematically as KPV, right?
Exactly. KPV.
It's like looking at a straw sitting in a glass of water.
That's a great analogy.
Because from the side of the glass, the straw looks bent or snapped. But the straw isn't actually broken, and the space inside the glass isn't bending.
No.
The water is simply denser than the air. So as light travels from the air into the denser water, it slows down and its path bends. The density creates an optical illusion.
Precisely. In the polarizable vacuum model, when starlight passes near our sun, the light bends around it.
Right.
Now, Einstein's math says it bends because the fundamental geometry of space has curved, but the PV model says the light bends because the vacuum's energy density gradient acts exactly like a giant optical lens in space.
So the light is just refracting through the denser quantum vacuum surrounding the star. Wait a second, though. A vacuum that gets thicker and thinner. A physical medium sitting in space that light travels through and refracts against.
I know where you're going with this.
Didn't Michelson and Morley completely debunk the luminiferous ether like 100 years ago?
They did.
The whole 19th century idea that space was filled with an invisible fluid to carry light waves was famously proven false.
Yeah.
So how is this polarizable vacuum not just a total rebranding of a debunked Victorian ether?
That is the immediate, glaring, historical red flag any physicist raises when they hear the phrase vacuum density.
It has to be.
But the sources draw a very hard, explicit line here. This is absolutely not the mechanical, static, luminiferous ether of the 1800s.
Okay, how is it different?
Michelson and Morley proved there is no stationary physical fluid that the Earth is dragging itself through, like a boat dragging through a swamp.
Right.
The polarizable vacuum is not a physical fluid. It is an electromagnetic reality driven by the quantum mechanical processes of virtual particle pairs. It is entirely relativistic.
Relative meaning.
Meaning it flawlessly obeys the speed of light limits and the observer effects that Einstein established. It's dynamic, not static.
So it's not a swamp we are swimming through. It's the energetic baseline of reality reacting dynamically to the fact that we simply exist inside it.
That's a beautiful way to put it. It is an isomorphic representation of general relativity.
Isomorphic. Let's break that down.
Isomorphic means the two models map onto each other perfectly. If you calculate how much light bends around a star using Einstein's geometric curvature, and then you calculate it again using the PV model's refractive index of the quantum vacuum,
You get the exact same answer.
you get the exact same answer. The macro outcomes are totally identical.
But, I mean, if they both give the same answer, why reinvent the wheel? Why do we need the PV model if Einstein already gave us the right coordinates?
Because Einstein's smooth geometric wheel cannot roll on the microscopic roads of quantum mechanics.
Ah, right. The infinities.
You cannot easily quantize a smooth, continuous curve. The math just shatters. But the PV model is already built out of quantum vacuum energy.
It's quantum native.
Exactly. It gives us a physical mechanism, vacuum polarization for how gravity works, instead of just a mathematical description of what the shape of space is. It builds the bridge.
Okay, that makes sense.
Mm.
We are swapping the smooth fabric of space for a refractive lens made of quantum energy.
Yes.
But this leads to a massive structural problem, doesn't it? We still have to use Einstein's equations. I mean, we know his math works for predicting the orbits of planets, the behavior of black holes, synchronizing GPS satellites, all of that.
We can't abandon Einstein.
Exactly. If we want to rewrite the foundation of gravity, we can't just throw out the chalkboard. How do we force this bubbling, granular quantum soup to play nicely inside Einstein's smooth, continuous equations?
To pull that off, the sources introduce a highly specific mathematical tool called the unit harmonic operator.
The unit harmonic operator.
Yes. Denoted by the Greek letter theta with a subscript t for time. The derivation charts in the source material actually feature a portrait of the 18th century mathematician Joseph Fourier because his work is the absolute backbone of this translation.
Fourier, as in Fourier transforms. The math used in everything from audio engineering to image compression.
The very same.
Wow.
A Fourier series is a mathematical way of taking an incredibly complex signal or pattern and breaking it down into a series of simple regular sine and cosine waves. We call those waves harmonics.
Okay, so breaking down complexity.
Right. Imagine hearing a symphony orchestra play a single massive chord. A Fourier series can mathematically separate that giant wall of sound into the individual vibrations of the violins, the cellos, the brass.
It deconstructs the complexity into simple vibrating waves.
Exactly. And Storti's framework utilizes a very specific application of this, a fully rectified square wave of unit amplitude.
Okay, you lost me a bit there with the jargon.
Fair enough. Without getting buried in the calculus, the core function of this operator is to mathematically quantize the number 1.
Wait, quantize the integer 1. How do you break apart the most basic number in existence?
Well, instead of treating the number 1 as a solid, continuous, absolute, like a solid block of stone, the unit harmonic operator rewrites the number 1 as an infinite summation of odd harmonic waves vibrating together in the complex plane.
Vibrating waves making up a single number.
Yes. If you add up an infinite number of these specific vibrating modes, they constructively interfere with each other perfectly, and the grand total equals exactly 1.
Let me try a digital analogy here just to see if I'm grasping the visual of this.
Go for it.
Einstein's math for the geometry of space-time is like an analog film photograph. It is perfectly smooth. There is no resolution limit. You can zoom in on the film grain forever, and it's just a continuous gradient of light and shadow.
A continuous manifold. Yes, that's Einstein.
And the unit harmonic operator is like taking that smooth film photograph, putting it into a high-end scanner, and turning it into billions and billions of digital pixels.
Yes.
From across the room, the digital photo looks exactly 100% identical to the analog film.
The macroscopic view is absolutely indistinguishable. When you are looking at massive systems calculating the orbit of Jupiter or, an apple falling from a tree, the number of these harmonic modes, the pixels in your analogy, is astronomically large.
Okay.
In the math, this is represented by saying n, which is the number of modes, is much, much greater than 1. Because n is so massive, the sum of those vibrating waves acts so completely like the number 1 that it is observationally and mathematically indistinguishable from 1.
But if this operator basically just equals 1 for anything bigger than a subatomic particle, why go through the grueling process of inserting it into Einstein's field equations at all? Because in the documents, it says Storti multiplies the Ricci scalar curvature term by this operator. First of all, what is a Ricci scalar? And second, if the operator just equals 1, doesn't multiplying by 1 just give you exactly what you started with? You haven't changed the equation at all.
So, the Ricci scalar, in the simplest terms, is the part of Einstein's equation that acts like a ledger. It's a single number that assigns a value to how much a specific volume of space has deformed or curved away from being perfectly flat.
Okay, so it's the curvature ledger.
Exactly, and you are correct on the macro scale. Multiplying the Ricci scalar by the unit harmonic operator doesn't change the macroscopic outcome at all.
Right, because anything times 1 is itself.
Exactly. For a planet, the operator equals 1. Einstein's classical predictions remain totally intact. The GPS satellites still sync up. We do not break general relativity.
So why do it? Why add this crazy layer of Fourier math?
What's fascinating here is what happens when we zoom in. Go back to your digital photograph analogy. What happens when you keep zooming in on a digital image, past the subjects, past the background, all the way down to the deepest possible level?
Eventually, the smooth image shatters. You see the grid? You see the individual squares of the pixels. It stops being a smooth gradient and becomes a discrete, blocky structure.
That truncation of those pixels is the key to the entire theory.
Truncation, so it stops.
Yes. There is a finite size to the smallest square. There is a physical limit where you cannot divide the image any further. In Storti's mathematical framework, we do not actually let n, the number of harmonic modes, go to infinity. We truncate it. We cut it off at a very specific, finite number.
Oh, And by truncating the harmonic expansion at the extreme microscopic scale, we stop the frequencies of the quantum vacuum from reaching infinity.
Exactly. We lock out the mathematical explosions.
You kill the infinities by enforcing a resolution limit on reality.
That's exactly what it is. When you use Fourier series to build a square wave, you get these tiny high-frequency mathematical jitters at the sharp corners of the wave. They're called Gibbs oscillations.
Gibbs oscillations, okay.
Think of it like the faint, blocky, ringing artifacts you see around text in a heavily compressed JPEG image.
Oh yeah, when the image looks crunchy.
Right. At a large scale, these jitters are so infinitesimally small, they vanish from any measurable reality. But at the extreme quantum scale, the fact that the wave is built out of finite, granular steps instead of a smooth curve is what actively prevents the math from spiraling into ultraviolet divergence.
Okay, that is a massive conceptual leap. We are saying that space-time, at its most fundamental bedrock level, is not a smooth sheet. It is built out of discrete, vibrating modes.
Right.
But that boundary, the exact point where the pixels stop and the resolution limit kicks in, how do we actually find it?
That is the challenge.
Because if a physicist just looks at the equation and arbitrarily decides, hey, let's stop the calculation at a billion modes just so the math works out, then we're right back to renormalization. We're just inventing mathematical tricks again.
And avoiding that trap is the true triumph of the electrographmagnetics framework. The cutoff point is not an arbitrary mathematical guess. It is a strictly derived physical necessity called the quantum vacuum spectral limit, or QVSL.
The QVSL, the infinity killer.
The infinity killer. The QVSL is the absolute physical boundary for these harmonic frequencies. It is the mechanism that actively prevents the universe from mathematically destroying itself.
Wow.
And it establishes this limit by demanding a non-negotiable physical equilibrium between matter and the vacuum.
Okay, equilibrium. What exactly is balancing against what?
To find this equilibrium, the sources utilize something called Buckingham pi theory.
Pi is in the Greek letter, right? Not the pastry.
Yes, pi. And Buckingham pi theory isn't actually a quantum mechanics concept originally. It's a rigorous dimensional analysis theorem developed by Edgar Buckingham in the early 1900s.
Oh, early 1900s. What was it used for back then?
It was primarily used in complex engineering and fluid dynamics. It is a way of determining how physical variables must mathematically relate to one another based purely on their fundamental dimensions like mass, length, and time.
Okay, so it's an engineering tool.
Very much so. Structural engineers use it to test scale models of bridges or aircraft in wind tunnels, ensuring the physics of a small model will scale up flawlessly to the real thing.
Wait, so Storti took a tool used to build bridges and airplanes and aimed it at the quantum vacuum.
He did. He applied strict dimensional analysis to the interaction between a particle and empty space. Using Buckingham pi, the framework proves that for any particle to be stable and exist in reality, its internal matter density must be in exact, perfect equality with the spectral energy density, the SED of the quantum vacuum, pushing back against it from the outside.
Okay, let me visualize this. So the matter density of particle pushing outward is balancing against the energy density of the bubbling vacuum pushing inward.
Yes.
It's like a deep-sea submersible.
Oh, walk me through that analogy.
So if you are sitting inside a tiny spherical research submarine at the very bottom of the Mariana Trench, the pressure inside the sub, the atmospheric air pushing out against the titanium hull, has to perfectly match the crushing hydrostatic pressure of the dark ocean outside pushing in.
Okay.
If the internal pressure drops or the hull is too weak, the sub just crumbles like a soda can. And if you somehow pump too much pressure inside, the sub would violently burst outward. In this scenario, the heavy ocean is the boiling quantum vacuum, and the submarine is a subatomic particle.
That is exactly the dynamic the math describes. Let's look at a proton, for example. A proton possesses a specific amount of mass energy concentrated within a finite, unimaginably tiny region of space.
Okay.
Without an external confining mechanism, that highly concentrated energy would simply diffuse outward into the lower energy void around it, and the proton would cease to exist. It would dissolve.
Just fade away.
Right. The only thing confining the proton, holding it together in a discrete package, is the ceaseless, chaotic creation-annihilation process of the vacuum, the literal pressure of those virtual particles hammering against it.
So the particle only exists because the vacuum forces it to exist.
Exactly. If the proton's matter density exceeded the vacuum's spectral energy density, the vacuum couldn't contain it and the particle would explode. If the vacuum's density were higher, the particle would be crushed into collapse.
But since we observe stable protons existing everywhere in the universe,
This equilibrium must be real. It is a mathematical theorem of existence.
And that equilibrium dictates the resolution limit of space.
Yes. The precise radial distance from the center of the particle to the edge, where these two forces perfectly cancel each other out, dictates the exact finite harmonic mode cutoff.
The edge of the submarine hull.
Yes. In the equations, this cutoff mode is denoted as nay. Beyond this specific harmonic mode, there are zero modes. None. The spectrum ends.
It just hard stops.
It hard stops, which entirely eliminates the ultraviolet divergences because you simply run out of harmonic modes before the energy can ever reach infinity.
This is incredibly elegant. It makes logical dimensional sense, but I mean, this is where the theoretical rubber meets the road.
It is.
Theoretical physics is a graveyard of beautiful mathematical theorems that made perfect logical sense, but couldn't be proven in a laboratory. Physics demands physical proof.
Always.
Can we actually measure this deep-sea submarine pressure balance? How do we know the QVSL isn't just an exceptionally beautiful mathematical fantasy?
The crucible of physical proof is exactly where this framework stakes its entire reputation. Storti doesn't just leave the QVSL as an abstract equation on a chalkboard.
Okay, what does he do with it?
He applies this exact dimensional equilibrium to real, measurable subatomic particles. And the results offer a shocking, paradigm-shifting resolution to one of the most frustrating, highly publicized headaches in modern physics.
Which is?
The proton radius puzzle.
Okay, let's dive into the history of this puzzle, because it caused immense drama in the physics community. For a long time, physicists thought they knew exactly how big a proton was.
They were very confident.
But then, around 2010, they started measuring it a new way, using exotic particles called muons instead of electrons. And suddenly, the proton appeared to shrink.
It was smaller.
The new measurements were about 4% smaller than the old measurements, which sounds tiny, but in quantum physics, a 4% deviation is a screaming alarm bell that your fundamental understanding of the universe is broken.
It was a crisis. Decades of accepted physics were suddenly under threat. But the source material uses the QVSL framework to derive what are called exact, closed-form analytical values for the radii of subatomic particles.
Closed-form analytical values, meaning they didn't measure the proton in a lab first and then reverse engineer the math to fit the results, right?
Correct. They ran the math purely from first principles. They used the harmonic equilibrium we just outlined, balancing the internal mass against the vacuum's spectral energy density, to blindly predict what the size of the proton and the neutron should theoretically be.
And what did the QVSL math actually predict?
For the proton, the framework derives a root mean square charge radius of exactly 830.59 atometers.
An atometer, that is 1 quintillionth of a meter.
It is unfathomably small. And for the neutron, it derives a mean square charge radius of negative 0.1134 femtometers squared.
830.59 atometers. That is an absurdly specific number. Does it actually map to reality? I mean, did anyone measure that?
It maps flawlessly to a very specific set of rigorous real-world experiments. In 2001, a massive multinational particle physics project called the CLEX Collaboration, which operated out of Fermilab and involved hundreds of scientists across several countries.
Okay.
They measured the proton's radius. Their result was 830.7 atometers.
Wow. 830.59 predicted by pure math, and 830.7 physically measured by a giant particle accelerator. That is virtually identical.
It is, and the success isn't limited to the proton. A 1995 experiment conducted by physicists Kopecky and Rees measured the neutron's charge radius at negative 0.113 femtometers squared.
And the math predicted negative 0.1134.
Again, a flawless, identical match with the derivation.
So the math works. The QVSL correctly predicts the exact size of the building blocks of matter. Why isn't this universally accepted? Why is there still a puzzle?
Because there is a massive point of friction with the established scientific bureaucracy. The official, globally recognized standard for physical constants is curated by an organization called CODATA.
The Committee on Data for Science and Technology.
Yes. Every few years, they release the definitive values that all scientists are supposed to use. And the official NIST 2022 CODATA value for the proton radius is not 830.7 atometers.
What is it?
It is 840.75 atometers.
840.75 versus 830.7. I mean, at the quantum scale, that is a canyon. That is missing the dartboard entirely.
It's a huge discrepancy.
So one of those numbers has to be fundamentally wrong. Is Storti just claiming that the CODATA standard is a mistake?
The framework argues that it is a fundamental misunderstanding of what is actually being measured by different experiments.
How so?
CODATA doesn't just run one single experiment. They aggregate data. The 840.75 value is a statistical average of various secondary electromagnetic radii.
Okay, electromagnetic radii, meaning...
Essentially, they are bouncing electrons off the proton and measuring how the proton's electromagnetic field scatters them. They are measuring its electrical footprint.
Right.
But the CLX collaboration and the QVSL derivation are measuring something deeply physically different. They are measuring the quantum vacuum equilibrium radius, or QVER.
The QVER.
Yes. This is the true structural physical boundary where the mass density of the proton perfectly balances against the spectral energy density of the vacuum.
Let me see if I can visualize the difference between those two measurements. It's like we are standing in a pitch-black room trying to measure the exact size of a glowing light bulb.
Okay, I like this.
The CLEX experiment and the new QVSL math are walking right up to the bulb in the dark and using cold metal calipers to measure the exact circumference of the physical glass bulb itself. That hard boundary is the QVER.
Yes, the physical glass.
But the CODATA standard is standing 10 feet away and trying to measure the size of the bulb by looking at the blurry, glowing edge of the light it casts into the dark room. That aura is the electromagnetic radius. CODATA is measuring the glow, not the glass.
That is a perfect visualization. And because CODATA averages multiple different measurements of that aura, the framework explicitly argues that it creates a mathematical blur.
A mathematical blur.
It is an artificial statistical compromise that obscures the discrete physical boundary of the quantum vacuum. And here is the critical consequence. If you take that blurry CODATA number and try to plug it into the quantum gravity equations, the math shatters.
Oh, because it's the wrong number.
Yes, it breaks down.
Yeah.
And you are forced to go back to using arbitrary renormalization tricks to artificially fix the infinities.
Wait. Let's play devil's advocate here. Is it really intellectually honest for the author of this new framework to just dismiss the globally accepted CODATA standard as a mathematical blur simply because it doesn't fit neatly into his equations?
That's a fair question.
I mean, if I invent a ruler and it doesn't match the standard ruler, claiming the standard ruler is blurry feels a bit like moving the goalposts, doesn't it?
That is the exact skepticism the wider physics community will apply. But Storti preempts this by providing an explicit mathematical proof to back up his claim.
He does.
Yes. He doesn't just throw the CODATA value out the window. He actually derives it from his own framework to show exactly how the illusion of the blur is created.
Wait, he uses the math that predicted the glass bulb to also predict the size of the blurry glow.
Exactly. The source documents detail a complex geometric model where the neutron is treated theoretically as a positive core surrounded by a negative shell.
Okay.
He uses advanced integration techniques and MathCAD simulation algorithms. And to be clear, MathCAD isn't a black box software that guesses answers. It is an industry-standard computational environment used by engineers and physicists to execute deeply complex calculus without human arithmetic bias.
Right, it's rigorous.
Extremely. By modeling that core shell geometry, he calculates the secondary electric radius of the proton, and the algorithm outputs a value of 848.6 atometers, which is a 99.1% match to the CODATA standard.
Wow. So he is mathematically proving I know exactly what the physical size of the proton is, and I know exactly why your instruments are being tricked into seeing it as larger.
The framework argues that the CLEX result, which has often been treated as an anomaly by mainstream physics, is actually the true measurement of the vacuum interaction. The tension of the proton radius puzzle only exists as you conflate the physical boundary of the vacuum with the electromagnetic form factor.
So if we accept that this subatomic math holds up, that the QVSL perfectly maps the size of a proton and a neutron by balancing them against the quantum vacuum, that is an incredible achievement on its own.
It is monumental.
But the mission statement at the beginning of this deep dive was unifying quantum mechanics with general relativity, unifying the microscopic with the cosmic. If this theory is going to rewrite the laws of gravity, the ultimate test is whether this exact same ruler can be held up to the night sky.
Scaling the cosmos. The transition from the micro to the macro is really where the electrogravimagnetics framework makes its most breathtaking, sweeping claims about the nature of reality.
Because we have our math tool, the unit harmonic operator, which quantizes the vacuum. And we have our resolution limit, the QVSL, which kills the infinities. How do you apply the math of a tiny proton to an entire planet or a galaxy?
The central thesis here is that the universe is deeply fundamentally self-similar.
Self-similar.
Yes, the exact same harmonic operators, the identical equilibrium equations that describe an invisible proton, also describe the Earth. They describe our sun, and they describe supermassive black holes like TON 618.
TON 618 is an absolute monster.
Yeah.
It is one of the largest black holes ever discovered in the observable universe. I think it's estimated at like 66 billion times the mass of our sun.
It is massive.
It's so large it practically breaks our models of how black holes can even grow.
Well, the sources provide a detailed comparative table mapping the QVSL parameters across these wildly different scales from the proton to TON 618. And the numbers reveal a completely counterintuitive pattern.
Okay, what do the scales look like?
For a single proton, the quantum vacuum harmonic cutoff mode, the number of pixels in our earlier analogy, is roughly 10 to the 16th power.
Okay.
The maximum cutoff frequency required to balance the proton is massive. It's 2,617 yottahertz. A yottahertz is 10 to the 24th hertz. It is an extremely high-frequency vibration.
So high frequency, but a relatively low number of modes.
Yeah.
What happens when you scale up to the Earth?
For the Earth, the number of harmonic modes skyrockets, as you would expect for a massive object, jumping to roughly 10 to the 28th power.
Makes sense.
But the maximum frequency drops significantly down to 519 yottahertz.
Oh, it goes down. And the monster black hole, TON 612.
The number of modes jumps to an unfathomable 10 to the 32nd power. And the maximum frequency drops even further, down to just 154 yottahertz.
Let me process this.
Yeah.
As the mass of the object scales up from a microscopic proton to a rocky planet to a galaxy-swallowing black hole, the maximum frequency of the quantum vacuum interacting with it actually scales down.
Yes.
That feels completely backward. Shouldn't a hyperdense, supermassive black hole require much higher frequency, higher energy interactions than a tiny single proton?
If we connect this to the bigger picture, you have to keep in mind what frequency represents in this dimensional framework. It represents the spectral energy density of the vacuum balancing against the object.
Right.
Picture the entire universe as a closed box containing standing waves of energy. In the very early universe, fractions of a second after the Big Bang, the box was incredibly small and unimaginably dense. All the energy of reality was packed into very few, incredibly high-frequency modes.
Like a dog whistle. A very intense, very high pitch.
Exactly. As the box, the universe expands over billions of years, the total amount of energy remains constant, but it is forced to spread out across a much larger volume.
Right.
Those few high-frequency waves stretch out and bifurcate. They split and divide into a massive bandwidth of much lower frequency modes.
Oh, wow.
So to balance a massive object today, like TON 618, the vacuum requires a staggering number of modes 10 to the 32nd power to sum up its mass energy equivalence. But because there are so many individual modes contributing, the maximum frequency required from any single mode is much lower.
Oh, I see. It is the difference between having a single $100 bill versus having 10,000 pennies.
Ha! That's exactly it.
The proton is the $100 bill. It has a high value concentrated in a single high-frequency item. The black hole is the pile of 10,000 pennies, a massive total accumulation of mass. But each individual harmonic mode contributing to it is a low-value, low-frequency penny.
The spectrum compresses as the mass energy density increases. The math effortlessly handles both scales. And this self-similar scaling realization leads to what is arguably the most stunning empirical victory of the entire EGM framework,
Which is?
predicting the Hubble constant.
The Hubble constant is the speed at which the universe is expanding outward. And if the proton radius puzzle was dramatic, the Hubble tension is a full-blown civil war in cosmology.
It really is.
Different methods of measuring the expansion of the universe keep giving astronomers wildly different answers.
The tension is severe. Back in 2008, the widely accepted standard measurement for the Hubble constant, curated by the Particle Data Group, was generally assumed to be roughly 73 kilometers per second per megaparsec.
73, a pretty high expansion rate.
But Storti decided to test his universal ruler. He applied the exact same QVSL equilibrium math we just used for the proton, the submarine balancing against the ocean, and applied it to the entirety of the Milky Way galaxy.
Wait,
He mathematically treated the entire Milky Way as a galactic reference particle.
how do you treat a swirling disk of 100 billion stars, gas, and dark matter as a single particle? What is the ocean of the vacuum pushing against in that scenario?
Well, in the math, you define a boundary. You calculate the total observable mass energy of the galaxy and map it to a spherical boundary, where the collective gravity of the galaxy interacts with the deep, flat, intergalactic quantum vacuum.
So you zoom way out.
You zoom way, way out. You balance the internal mass density of the Milky Way against the external spectral energy density of the cosmic void. By solving for that equilibrium, Storti predicted the expansion rate required to maintain stability of that interaction.
And what did he get?
In 2008, he published a predicted Hubble constant of exactly 67.08 kilometers per second per megaparsec.
He bet against the global consensus of 73.
He did. And then 5 years later, in 2013, the European Space Agency's Planck satellite, which is the most precise cosmological instrument ever built at the time, designed specifically to measure the cosmic microwave background. It released its first massive data set. The Planck satellite completely bucked the 2008 consensus. It measured the Hubble constant at 67.3.
67.08 predicted from pure math. 67.3 measured by a billion-dollar orbital satellite 5 years later. That is unbelievable.
It is a stunning validation.
We essentially used a ruler designed to measure the invisible boundary of a proton, held it up against the void of intergalactic space, and it gave us the exact right answer half a decade before our best technology could verify it.
And the framework accomplishes the exact same feat by identically predicting the cosmic microwave background radiation temperature. And the crucial point here is that this is not a retrodiction.
A retrodiction.
A retrodiction is when physicists take new satellite data and then tweak the variables in their equations until it matches the new observation. Storti made a genuine a priori prediction derived completely from first principles.
Meaning he didn't peek at the answers before doing the math.
Exactly. It heavily implies that the universe is a single, coherent, deeply interconnected system. The macroscopic cosmos is inextricably linked to the microscopic quantum vacuum.
But, I mean, if the universe really is this deeply self-similar, and space-time is fundamentally granular, built out of these discrete, vibrating harmonic modes at every possible level of scale that has to change how we experience physical reality on a daily basis.
It absolutely does.
What does a quantized, granular space-time mean for gravity, right here, right now, sitting in our chairs?
It means that gravity is not what we perceive it to be. Because the gravitational field is constructed out of a finite number of discrete harmonic modes, gravitational acceleration cannot physically be a perfectly smooth, continuous curve.
It can't?
No, it is quantized. It happens in discrete steps.
Steps. Are you saying that if I drop my coffee mug right now, it isn't smoothly accelerating toward the floor?
The framework predicts that objects falling toward the Earth are actually accelerating in discrete, infinitesimally small increments. It calculates the root mean square gravitational acceleration increment at the Earth's surface to be roughly 10 to the negative 28 meters per second squared.
10 to the negative 28. That is a decimal point followed by 27 zeros. Let's ground that number. That is so small that if you compared it to the width of a single human hair, or even the width of a single atom, it would still be almost incomprehensibly microscopic.
It is phenomenally, unfathomably small. To your human eyes and to every single macro instrument we currently possess, the coffee mug appears to fall in a perfectly smooth, uninterrupted curve.
It's the difference between walking down a smooth concrete ramp versus walking down a staircase where the individual stairs are smaller than protons.
Yes.
My foot would never feel the edge of the stairs. My brain would just register it as a perfectly smooth ramp.
The discreteness only applies to the extreme spectral decomposition of gravity. But this brings us to a mind-bending technological implication.
Oh, already.
We defined gravity earlier as a product of the polarizable vacuum, the refractive index, the KPV, the optical illusion of the straw bending in the water.
The denser vacuum bending the path of light and matter.
Right. Well, the source documents introduce something called a PV transformation matrix. If the curvature of spacetime is actually just a refractive index that relies on electromagnetic energy density, it implies that humans could, theoretically, design technologies to locally manipulate this index.
Manipulate gravity.
By superimposing specific, highly engineered electromagnetic wave functions, we could artificially alter the vacuum density in a localized, confined area.
Wow.
The sources formally dubbed this concept metric engineering.
Metric engineering. We are talking about warp drives. Anti-gravity plating. Are we looking at the blueprints for building UFOs here?
In absolute theoretical principle, yes, the physical pathway is outlined in the math. If gravity is an optical illusion created by vacuum polarization, and you can artificially polarize the vacuum using advanced electromagnetic fields, you can engineer gravity.
That's insane.
You could make an object fall up or sideways by tricking the vacuum into believing there is a massive object nearby.
Okay, I have to inject some reality into this, though. We are talking about measuring or manipulating an acceleration step of 10 to the negative 28 meters per second squared.
True.
We absolutely do not have the technology to measure that. We might not have the technology for centuries simply because the ambient thermal noise of the planet, or like a tiny seismic tremor from a truck driving down the street, would completely drown out a signal that small.
It would.
If we can't test it, if we can't build this metric engine in a lab today, isn't this all just beautiful philosophy rather than hard science?
It is a totally valid critique, and it is the exact same empirical hurdle that string theory has been failing to jump over for 40 years. But Storti defends the framework by pointing to the internal consistency of the math.
The internal consistency.
The equations are validated by those rigorous MathCAD algorithms provided in the text. The simulation proves that the massive cosmological constants like the Hubble expansion and the tiny particle properties like the proton radius emerge naturally from the exact same fundamental sequence of pi math without requiring any arbitrary tuning or human meddling.
So even if we can't build the microscope powerful enough to see the microscopic stairs of gravity yet, the fact that the math for the staircase perfectly predicts the size of the entire building gives it immense validity.
Exactly. The internal technical consistency is structurally reinforced. You don't need a set of independent, hand-picked mathematical parameters to make the galaxy work, and a completely different set of parameters to make the atom work.
They use the same ruler.
They are mathematically inseparable, which forces us to look at how this theory fares against the established heavyweights of theoretical physics.
Because if the EGM framework is this perfect, why isn't every physicist on Earth adopting it right now? What is it competing against in the academic arena?
The sources explicitly dedicate space to comparing the electrogravimagnetics construct against the mainstream giants of quantum gravity. You have loop quantum gravity, or LQG. You have string theory.
String theory is huge.
You have asymptotic safety, causal dynamical triangulations, and group field theory. These are the colossal models that receive the billion-dollar funding grants and get featured on the covers of science magazines.
Let's look at string theory, since it is the most famous. It proposes that reality is made of tiny, vibrating strings of energy operating across 11 different dimensions.
String theory is mathematically gorgeous, but it suffers from a fatal flaw. It relies on abstract minimal length scales, the Planck length, and extra dimensions of space that are curled up so tightly they cannot be observed.
So you can't test it.
It completely lacks empirical grounding. You cannot test it in a particle accelerator.
What about the others?
Loop quantum gravity is another major contender. It successfully discretizes space, turning it into little interlocked loops, but it lacks empirical hadronic inputs. It doesn't naturally spit out the size of a proton the way EGM does. Asymptotic safety relies heavily on that complex, non-perturbative renormalization we talked about at the very beginning, forcing equations to flow to a theoretical fixed point just to avoid the infinities.
So string theory is like writing a perfectly flawless, beautiful new language with immensely complex grammar, but nobody in the actual universe speaks it. While EGM is a slightly messy working dictionary for the practical language the universe is already using.
EGM's supreme advantage is that it is anchored in observable physical SI units. It uses real-world hadronic radii that you can physically measure in a lab. However, the text is intellectually honest. Storti explicitly addresses EGM's current limitations.
It have flaws.
It is currently incomplete in one highly specific, highly complex area. It simplifies aspects of nonlinear graviton self-coupling.
Nonlinear graviton self-coupling. Okay, I'm going to need you to break that down.
In standard quantum gravity models, the hypothetical subatomic particle that carries the force of gravity is called the graviton.
Okay, gravitons.
Because gravity fundamentally interacts with all forms of energy, and gravitons themselves possess energy, gravitons should theoretically interact with other gravitons.
Oh, I see.
It creates an infinitely recursive, massive, tangled web of self-interaction. The EGM framework, in its current foundational state, simplifies these interactions to make the initial math workable. It leaves full, nonlinear quantum dynamics for future perturbative expansion studies.
But wait. If EGM hasn't solved nonlinear graviton self-coupling, isn't it technically an incomplete theory? Why should the physics community abandon decades of institutional momentum on string theory to adopt an incomplete EGM model?
This raises an important question regarding what we value in physics, because no model, including string theory, loop quantum gravity, or asymptotic safety, has successfully solved the nonlinear graviton treatment in a single comprehensive manuscript.
Nobody's solved it.
No. EGM offers something profoundly better than an elegant but untestable mathematical landscape. It offers an engineering pathway that matches laboratory data today. It predicts the Hubble constant today. It solves the proton radius puzzle today.
It's the difference between a beautiful, flawless blueprint for a glass castle that is physically impossible to build, and a slightly incomplete blueprint for a sturdy brick house you can actually live in right now.
That's a great analogy. The realization that modern physics may need to trade elegant, untestable mathematics for an empirically anchored, engineered reality sets the stage for a massive paradigm shift.
We have covered an incredible amount of ground today. We started with the empty box, the quantum vacuum, and realized it is not a void at all.
Not even close.
It is a boiling, effervescent fluid of virtual particles constantly popping in and out of existence via the creation-annihilation process.
The energetic baseline of reality.
Then we introduced matter into the box. We learned that a star or a planet doesn't just bend the fabric of space. It polarizes the bubbling vacuum, creating an energy density gradient, an optical lens of gravity that slows down light and matter.
The polarizable vacuum model.
Then we looked at how to translate this into Einstein's math, the unit harmonic operator. We effectively scanned the smooth analog photograph of general relativity and turned it into a digital picture made of discrete, vibrating harmonic pixels.
Yes.
And by establishing the quantum vacuum spectral limit, the QVSL, we figured out exactly where those pixels stop. We used the deep-sea submarine balance of internal mass density and external vacuum pressure to establish a physical limit, killing the mathematical infinities that have plagued physicists for a century.
And doing it without relying on the arbitrary mathematical tricks of renormalization.
The ultimate proof of this framework is that this simple equilibrium scales perfectly. It explains the exact 830.7 atometer size of a proton measured by the SELEX collaboration.
Perfectly matched.
And staggeringly, if you scale the exact same ruler up to the size of the Milky Way galaxy, it correctly predicts the expansion rate of the cosmos, nailing the Planck satellite's Hubble constant measurement half a decade before the satellite even launched.
It proves that the macroscopic cosmos and the microscopic quantum vacuum are inextricably linked.
Which means the gravity holding us to the Earth isn't smooth. It operates in unimaginably tiny, discrete steps, hinting at a distant future where humanity might use metric engineering to artificially manipulate gravity itself.
A wild thought.
So the next time you accidentally drop an object, a pen, your keys, a coffee mug, and watch it fall to the floor, remember that it might not be gliding smoothly through empty, curved space. It is actually vibrating its way down an invisible subatomic staircase created by the seething quantum vacuum.
It profoundly changes how you visualize the physical space occupying the room around you.
So what does this all mean? It shows us that the universe is deeply mathematically self-regulating. It perfectly balances the infinitely small with the unimaginably large, using the exact same fundamental language. We just had to learn how to read the dictionary.
I want to leave you with a final thought to mull over. We talked extensively about that perfect equilibrium, the deep-sea submarine, balancing against the crushing pressure of the ocean.
Right.
If the mass of a single proton perfectly mirrors the spectral energy density of the entire surrounding vacuum, then in a very real physical sense, the particle doesn't just casually exist in the universe.
What is it doing?
The particle and the universe are constantly, violently negotiating each other's existence in real time. What happens to the entire fabric of the vacuum if we eventually figure out how to artificially alter that equilibrium?
That is a terrifying and brilliant blueprint that I am not sure we are ready to build. Thanks for taking this journey with us today.